Ah, cara, eu passei com um dia desse aí e depois vai todos nós ligados. Principalmente aqui.
Yes, I get it.
Just not stable. Okay, thanks. Are they turned on? Hello everybody. I'm sorry for being late. Let's start from analyzing the problems of the previous day. Then after the break I want to have a talk on the computational geometry. But to save time for this talk, again I'm probably going to skip one or two problems and then send them. When I'll make the written analysis of all that I owe you, I'll add these problems here. But now we need to save time for the lecture. Okay, so let's start with the easiest problem. It's a discussable question which one was the easiest, but I suggest it was problem B. So, problem statement was that you are given a sequence of 1s and 0. And two operations that you might do is first take the first character, first letter, and flip it. If it was 0, replace with 1. If it was 1, replace with 0. This costs, like, as I remember, 4. But that actually doesn't matter. Anyway, we are going to try all the possibilities. And another way was to shift the string one letter left or right. So take one character from here and put it to the end, or take one character from the end and put it to the beginning. And that operation costed 7. And the goal was to turn the whole string to zeros or to ones, I don't remember, using as minimum cost as possible. So natural formulation. To solve the problem, I'll draw all this in another way. I'll place all these characters this lattice on the circle. And there is one special position of the circle such that I can change the character. Yeah, of course, obvious observation, we only replace ones with zeros. We never need to replace 0 with 1. So we can like rotate this wheel and change letters. And now, what are the strategies? What's the approach here? The idea is that we do not need to change the direction of rotation too many times. Like, it doesn't make sense to do something like turn it a lot to the left, then turn it a lot to the right, then again turn it a lot to the left. Because we can notice that all these operations, they can be replaced with only one rotation to the left and, okay, no more than one rotation to the left, no more than one rotation to the right. Because we can take any two rotations to the left and say that we need to use only one of them. We can combine them to have only one. So, first obvious strategy is to just replace all ones with zeros and rotate in one direction until there are any ones remaining. So that's equal to going to the right to the first one. To the last one in counterclockwise direction. Then what will be the cost of this operation? It will be 4 multiplied by number of ones. But actually 4 multiplied by one number of ones, this is the value we pay in any strategy. So what really, so we already know how many operations of replacing one letter with another will perform. The only thing we need to minimize is the number of rotations. So how many rotations do I perform? I mean unit rotations in this case. Only the distance along the circle to the first one in clockwise direction. So here's the first one that I meet. That means I perform the length of the circle minus this distance. And along doing so, I replace all ones with zeros. Second case is symmetric. We just rotate clockwise until we replace all ones. And now what is combining two rotations? That means to some point I rotate counterclockwise, replace all the ones, and then I will rotate counterclockwise. Oh, sorry, vice versa. This is counterclockwise, this is clockwise. When can this case be more productive? For example, if the string looks like almost all zeros and some ones on its ends, yes. So that means you need to rotate a little to the left, then rotate a little to the right, and you're down, instead of making the full flip. How to choose which position to take? Like, what's a greedy idea here? Actually, you should not care about the greedy idea, as the number of possibilities is linear. So instead of trying to find which one is better, you may just try all of them. Like, if you pick any position, then surely what you need is, okay, imagine you pick any position and you want to say that, okay, I do not rotate the wheel over this position. That means I'll stop at the first one in this direction and first one at this direction. And now just a simple formula. Like, if you, for example, choose to rotate clockwise first and then counterclockwise, then you pay twice this distance plus this distance, or twice this distance plus this distance. So you just check. Well, actually, you even do not need the first cases I mentioned. You do not need to try rotating only left or only right, because if you pick positions here, that automatically will be equal to rotating only counterclockwise, and if you pick this 0, it will be equal to rotating only clockwise. So actually you should not deal with the cases. I think that's all about this problem. Maybe it was a bit more difficult than the easiest problem we usually had, but as you noticed, the whole contest was more difficult. I don't think there are any difficulties with understanding or inventing the solution here, but implementing, there may be some implementation details. I don't know. Any questions about this problem? No. Okay, then goal C. I'll go back to it later. Yeah, G. I think G was the second easiest problem, or at least among second easiest problems. But it featured some tricky cases that you do not need to forget. Because this is the case when you think, okay, I know how to solve this problem in general case, but I need to treat with some smaller cases. But then it turns out that smaller cases are the problem actually, and general case is not. So what's the general case? Like, it's not right to say that this case is general, but what additional restriction may we add on the input that will make the problem much, much easier? If we say that all A are distinct, like there are no equal values. If there are no equal values, you can actually treat them as a permutation. And what you need to do is, in some permutation, like find the answer, but how does the answer look like? So imagine I have this permutation, and let's take a look at positions that we ever are going to touch. Like we can split all the positions in two sets, like the one I'm not going to touch at all and the one I'm going to move. Obvious observation is you never apply move operation twice to one element. That can always be replaced with one, maybe by changing order. So here are some elements that we are going to move. That means the resulting array will look like part of these elements that we choose to move to the left, then elements that we decided not to touch at all, and elements that we decided to move to the right. And we want this to form an increasing sequence. Like, what does it mean? First, it means that, okay, 1 and 3, I can make them increasing just by changing the order. But I need to pick such a subset as the elements that I do not touch, second, that first of all, they go in increasing order, and second, the biggest element I do not touch is smaller in here and same here. So actually, I need to find the longest subsequence in the original sequence, such that if I write the subsequence out, it forms the part of the sorted array. So I need to find a subsequence of elements such that they go in the order they should go in the sorted array. Like, for example, if I have element 3, then here I have element 5, but somewhere I have 4. Then taking 3 and 5 is not the good subsequence. Because, yes, they still go in the same order in the sorted array, but I need this to be continuous segment, not subsequence of the result. Okay. So, for example, 3, 5, and here comes 4. So how do I choose the longest subsequence that goes in the right order? That's pretty easy. We just need for each element to decide whether the element that should follow in the sorted array, whether it stands behind or before or after my element. So I build an array like, let's say, good, and it's equal, like imagine, okay, its value is 1 if the element that goes next to me, next to A, is in the sorted array, it goes after it in the original array. Now I have array of zeros and ones, and what I have to do, I have to pick the longest segment consisting of ones. So any continuous segment of ones now corresponds to some subsequence. Some subsequence that I can use as the second. Yes. Oh, no, it's in my bag, actually.
I'm sorry. In this tutorial line, it's okay. It's just the class name.
This?
Yes. Thank you.
Okay, I'll try to speak loud. So yeah, if we see that any segment of ones, it corresponds to some subsequence that we can use as the second part of the answer. That means the result is the length of the whole sequence minus the length of the longest segment consisting of ones. But that's not completely the case of this problem. Actually, this is not at all the case of this problem, because here equal elements are allowed, and that makes everything way interesting. Still, let's take a look at the results. Not the results, at the resulting sequence. So, this was my original, and this is the result. I still can split it in 3 parts. So, the elements I move to the front, elements I move to back, and elements I do not move. Now let's split. Let's take a look at how this sequence looks like. So there are some groups of equal elements. What we can surely say we can say that all the groups except the first and the last consist of all elements with this value in the initial array. So it may be possible only if the latest element in this group goes before the latest element in this group. Like if these were values 3 and these were values 4, then again I should check that the first 4 appear after the last 3. And for beginning and ending group, this is actually not the case. Because, for example, there might be some 2's after 4. But what I do is I pick them to the first set. And that means I move them to front. So what we do is we should try. If like for example, first imagine that I fixed values like I know that the smallest element that will such that all appearance of this number will occur is 3 and the biggest is 4. Then I should decide how many, like let's say here are 5 and here are 2's, how many 2's and 5's I can use. That's okay, because I know that here comes the latest appearance of 4. So I need to find the latest appearance of 4 and then just take as many 5's as go after it. That's easy part. Same with 2's. Like I need to find how many 2's are located before the first 3 and just take them all. It actually works fine, but there is one more case. There are actually 2 more cases that we need to treat. And who knows what are the cases?
When you don't have the middle, so you can move. When you don't have a middle segment.
Middle segment?
Yes, like you have 3 and 4.
Yes, you're right. Then I do not have this 3 and 4. I only have some elements at the beginning and some elements at the end. In this case, I cannot behave greedily. Let me draw an example. So, for example, 1, 1, 2, 2, 1, 1, 1, 2, and let's say 2, 2, 2, and then here one more. Yeah, that's it. So 2 greedy approaches. First, take all 1's, and then take all the 2's that go after the last one. They give you 7 1's and 1, 2, 8. Then take all. I should add 1 to here. So taking all 2's and then 1 will give you 8 as well. But if you try all the positions to break this sequence, for example, you break here and then you take all 1's to the left and all 2's to the right, you can get 10. That's a way better. So you cannot behave greedily. You just need to take all 1's and say, what is the answer if this 1 is the last? That means you need to take number of 1's before, and this one too, and the number of 2's after. Also, there is a case when in the part 2 there is only one number, but it's like this case will automatically be tried by this case, just when the second sequence has size 0. Okay, so I think that's it with this problem. Any questions or comments? Or maybe someone did it in a different way. Okay. We still have time to ask questions while I'll put this on. So now you do not have time. Let's pick one more problem to analyze. H. Off? No. But nothing changed for you. Okay, if anyone has any trouble hearing me, raise your hand. We will try to do something with this. H. Okay, so you are given n participants, and each of participants, it was assigned some score on line round, and also you know the scores assigned to participants on the on-site round, and you want to know what is the minimum place, like what is the lowest place you need to take in order to guarantee that you can still make it to the best x. And your place is counted as 1 plus the number of players who have strictly more points than you. More or less, I think more. Okay. How do we check? In the worst case, yes. Also, it said in the worst case. Usually when problem says in the worst case, it turns out to be, okay, no, actually it can be anything. It can be dynamic programming, it can be greedy solution. It's not average case, but never mind. Let's see what is the lowest place we can take if, for example, we know we placed on, like, P is the place we took on online round. Oh, sorry, for online round we already know the number of points we have. P is the place we took on the offline round. I mean, on site. So we can behave greedily. Like, we know who can overwhelm us, who can be better. Of course, it makes sense to say that some people who did, top people who did their best on online round, they will be the one to overwhelm us on the on-site round. So if I sort by A are the values achieved on online round. So here comes, like, K is my value. So we first will try to choose people who beats us in overall score among the best on among the best during the on-site round, online round. So the person to beat us more likely is the first one, the one who gets the biggest score during the online round. And now we can assign him the best value of on-site round, and then he surely wins. But that doesn't make sense, as we do not care actually how many points we lose to him. We only care that he has more points than we do. So what we need to do, we need to pick minimum. Okay, I'll look at these in the sorted order as well. So which value of B should I assign to the best person of online round? That should be the smallest B, such that the sum is strictly greater than my score. That's pretty easy to show that any answer can be found in this form. If it's not so, just take a look at the answer. You will be able to replace some positions. Okay, now I pick the second best person of online round, and among the remaining elements, I assign him, let's say, best value among yes, a best no, sorry, not the best, but the minimum possible B among remaining, such that his sum is strictly bigger than mine, and so on. Then I do the same with the third person, fourth, and so on, until I succeed, until I can assign such value of B, so it will be better. That's what my place if I take position P. But my position is actually not given in the statement, and I'm interested in what's the maximum P, but I still can guarantee to fit in first X. If you, the usual trick, like not trick, the usual approach, when you are asked to maximize something or minimize, is to transform optimizing problem of optimization to decision problem. So what's the decision problem? Is if I take the place P, can I get in the first X? That's the decision problem. The answer is yes or no. Of course, you all know the way to transform one problem to another. It's to use binary search. In this problem, because of course we know if taking place P will be enough to guarantee position in first X, then of course you can say that taking place P minus 1 will still be enough. So you do binary search and that's it. But that's actually a pretty brute force approach to this problem. Like, what I can do? I can solve for fixed value of P. What I can do? I can do binary search. I combine them, I get solution, I do not think. But I think you can actually solve the initial problem, yes, for the, like. So who solved this problem in a different way without binary search? No one. Okay. Well, I only thought that there may be another solution. I didn't think of it, so I'm not going to analyze it. So any questions? No questions. Okay. Then, what comes next? G I already analyzed. H already. I think problem J comes next. Okay, this is the number theory. I hate it really much. Though this problem about number theory was that easy that even I managed to solve it. Who wants to share his solution? Yeah.
Problem J, right?
Hmm?
Problem J.
Problem J, yeah.
Well, basically, you had n jelly beans, and you wanted to eat them in n days. And you wanted to make sure of two things, that either n was divisible by n, or that the remainder of n modulus m was divisible by n, but n was divisible by the remainder of these. So of course you could brute force it, but it's 10 to the 12, so it's time limit exceeded. So what I realized is that first, every single divisor of n has to be part of the answer. So let's just call all the divisors of a d, and if we choose one, it's like d sub I. So I realized the following: if we have n is congruent to 0 mod d sub I, right? Because it's a divisor. So if we do the following, n minus d sub I, it also has to be congruent with 0 modulus d sub I. So what I did is, for every single divisor of n, I applied n minus d sub I, and I got all the divisors of all these numbers, and now for every single of those numbers you can actually like do this, since there are a limited amount of numbers, and you just count once every number that fulfills this condition. And that was my solution.
So the solution is you tried all divisors of
n.
n.
And then I did n minus each of the divisors and got all the divisors for all those numbers.
Yes.
And then I checked this condition, and if this condition was fulfilled, I got the number. I first tried a set, but I was getting time limit exceeded, so I stored them in an array, then sort it and count just the different ones.
Okay, but actually I think there are some additional. You also need to check that like the order is like at least it should be greater than m. Oh, it should be smaller. Okay, never mind. So yes, you tried all divisors of n, then you subtract and try all divisors of this number.
Yeah.
But like, how long does it take? Have you any ideas?
Well, it's pretty fast. I actually tried a highly composite number, and it takes like around 1 second or something in my computer.
Yeah, what's like? You used which technique you used to find all divisors?
To find the divisors, okay, I did first, if the number I had was bigger than 40,000, I just chose 40,000 because it's a big enough number. Sorry, 1 million, because 1 million is a nice number. I just tried to get all the numbers via a sieve, which was basically pretty fast. Because if it's lesser than 1 million, then you just get all the divisors like straight up. And if it's bigger than 1 million, then I had to iterate through all the primes. So if it's bigger than 1 million, then yeah, it was pretty slow.
Okay, thank you. Let me speak for a while on some ways to fasten finding all divisors. Of course, not in general case. No, there are ways to fasten factorization of number in general case, like Lemon's method, Rho method of Pollard, and so on. But that's the stuff that might be pretty hard to implement during the contest. And second, well, I have never seen anyone using this, anyone who required this algorithm during the 5-hour contest. We used to ask school students to implement it, but on the contest that lasts for 2 months. But here are some tricks for cases when you actually need to try many times. Like then you have to factorize numbers many times. Okay, I'll erase this. So, first approach is just square root of n. That's actually not a polynomial algorithm, because as you probably know, there is no polynomial algorithm to factorize number. Okay. And actually, if one day there will appear one, I will really care about all the security in the world. So, second what we can is Eratosthenes seed. If I might mistaken in the names, but when you have an array and what you do is first you consider all numbers in the array to be prime except 1. Then you take first 1 and multiply it. So now for all the numbers of form e multiplied g until the end, you mark them as not prime. So how do you call this? See, but yeah, okay. So it's work time. The easiest bound is n log n. If you just write the sum of harmonic values, harmonic sequence. But actually, you can notice that you do not sum all the values here. What you really do is you sum only 1 divided by some prime number. And that sequence has value n log n. So the second approach will take n log n to precalc, and then log n to factorize the number. If the number is not bigger than n, of course. Because actually what you can do in this approach, instead of just marking 0 or 1, if it is prime or not, what you can do is you can calculate the minimum prime divisor. So the ith will be the minimum prime divisor of value e. And now to factorize any number, you just move to the beginning. So you divide number by its minimum prime divisor until you get to the beginning. That works in log time. And then you know factorization, you may try all the divisors. That will work, of course, in time equal to the number of divisors. A way to fasten it is to use linear sieve instead of this one. There are plenty of them. Like I've read about 3 different ways to do this in linear time. You can read in the internet. But there is one more trick that is not so obvious. Probably one day you will need it, so I'll tell it to you. It actually takes all square root from n to precalculate, but then for any value that is less or equal for any c that is less or equal than n, we can find its factorization in square root of C divided by log time. And that may really save your time limit one day. So what's the idea? That when you, how does the simplest algorithm that like checks whether the number is prime or finds factorization this time works? It just takes all the integers from 2 to square root from n and checks whether n is divisible by this number. But of course, we know that we only need to check prime numbers on this segment actually. So instead of trying all numbers from 2 to square root, what we do is we try all prime numbers from 2 to square root. And as you know, the number of prime numbers, the quantity of prime numbers on segment from 1 to n is, has the order of n divided by log n. So that's it. That will really fasten like, I think, 10 times maybe or so. Any questions on this tricks? Okay, if no questions on the trick, we should move forward to other problems. For those who were late, I already mentioned that as I want to talk about computational geometry, maybe 1 or 2 problems will remain for written analysis, which I'll send to you as soon as possible. But still, there are some problems who no one managed to solve, and I want to analyze them. I think I should start from problem A, because it was the next most accepted problem in the standings. Actually, you might disagree, but I consider problem A to be one of the stupidest problems in the contest. Like, not stupid, it's a bad word, but the one that didn't require to think, actually. If you are familiar with suffix structures like suffix array, suffix tree, or suffix automaton, then you can easily figure out how to solve this problem. So it just requires you not the ideas, but the knowledge. And also some coding skills, of course. First, let's read the statement. What does it say? It gives us that strange description of good string that on any prefix, the number of ones or zeros, I don't remember, is zeros. It's strictly, there's no less than the number of ones on this prefix, but then for any suffix, the number of zeros is less than the number of ones. Of course, that's just a definition of correct sequence of brackets. So that is, you want to find the longest refrain that is a correct sequence of brackets. A refrain, at least I know it as refrain, is this function, like the word that has a maximum function of occurrences multiplied by the length. So before we proceed to finding the longest refrain that is, not the longest, finding the maximum refrain that is correct sequence of brackets, let's just solve the problem of finding the maximum refrain. Who of you are familiar with suffix structures? Any? Like, which one? Array and tree. I prefer automaton, but the choice is up to you. Anyone else? Like, array. Well, actually, This problem is much easier to solve using tree or automaton. That's array still works. Okay, I think I have to spend some time at least to tell you what they are, so you know what to Google. What is suffix array? It is sorted array of all, okay, there are two definitions, two different approaches to suffix array. First is, suffix array is the sorted array of all suffixes of the given string. And second is, suffix array is sorted array of all cyclic shifts of the given string. Which one to pick? It depends usually on the problem, but they can both be transformed to each other, of course, in linear time, so it doesn't matter. Actually, they are usually transformed by placing some unreadable character at the end. Like, if I can sort cyclic shifts, then I can just place this character at the end. It will be equal to sorting suffixes. And if I know how to only sort suffixes, then I can double my string and then take sorted array of its suffixes and take only this who start here, and this will be array of cyclic shifts. So it doesn't matter a lot, but in the original algorithm, I think they used to build array of cyclic shifts. So never mind, in this problem we need suffixes. Okay, so it's sorted array of strings. Well, of course, the total size of all suffixes of the string has square order. So instead of storing the whole strings, I'll just store the position of the first character. For example, if I have string, like let's say this one, so how does the sorted array of its suffixes looks like? This is 1, 2, 3, 4, 5, 6, 7. The smallest suffix is 7, because if one string is prefix of another, then we consider the shortest one to be lexicographically smaller. So first comes 7, then comes 5, then comes 1, then 3, because you see 1 is smaller than 3 because AB is smaller than AC. Then comes 6, 2, and we finish with 4. So that's the suffix array. I'm not going to talk now about how to build it, also you can easily read it. But to solve problems using the suffix array, you also need some additional function called LCP, longest common prefix. So LCP is for any two neighboring suffixes in suffix array, we calculate what is their longest common prefix. And now the best fact is that if you want to calculate the longest common prefix of two strings, you just need to pick minimum value on this segment. And that will be their LCP. That's pretty obvious actually if you look at the trie of these suffixes. Like, take all the suffixes and put them in a trie. That will be A, B, A, C, A, B, A. Then it will be just A. A, B, A. Okay, maybe I should choose different example this next time. A, B, A, A, C, A, B. B, and BA, BA, CBA, and finally C. A, B, A. Okay. That's a bad example. Okay, I give up. It doesn't show anything actually. But if you draw a trie of a string, then you can see that actually longest common prefix is equal to LCA in a trie. They even like look similar, LCP, LCA. So, and that's why this algorithm also works. So as you know, LCA is minimum. It can be calculated as minimum. So you can reduce LCA problem to range minimum query problem. That's it. Now, how do you solve? Okay. Also, what is suffix tree? Suffix tree is just a trie of all suffixes, but not that kind of trie, but compressed one. Like there is a compressed trie, then on any node, instead of starting one letter, you start two indexes that correspond to some substring. Like here it would be, okay, from 1 to 1, then from, this will be 1H with 2 free written on it, and this will be one more H with 4 7 written on it. This all will be replaced with 1H with which one was it? AC. Okay, so this has 4 to 7. Here is 2 3. Here comes 4 to 7. And here comes 4 to 7. One, 2, 3, 4, 5, 6, 7. Okay, I have 7. Ending point seems to be correct. So that's compressed trie. And it's pretty easy to show that compressed trie, the number of nodes in it is linear. Because if you have a node, you have either suffix ending at this position or something splits. And there is a pretty simple statement that if you have some subsets I, such subsets like some sets S that are all subsets. Okay, no mind. You just have sets S. And such that for any I and J, two subsets, they do not cross, or one is the subset of the other. So this is how you can actually describe the trees. For any such kind of sets, if the total number of different elements in all sets is no more than n, then you can show that there are no more than 2n such sets. Okay. No, that actually doesn't matter, just to tell you. Yeah, I don't think you need this to analyze suffix tree. It's pretty obvious it has linear size. But this can be useful to analyze right contexts in suffix automaton. Okay, this is suffix tree, and it's the hardest one to code among all the suffix structures. But from the other hand, it's the easiest to work with. Like, if you do not know how to solve the problem on the suffix tree, then you won't probably figure out how to solve it on the suffix array. And suffix automaton is actually a thing standing a bit outside. It really solves different sort of problems. Suffix automata is the smallest automata that finite determined automata that takes all suffixes of a string and only them, that accepts only suffixes of the string and only them. So I'm not going to work with it today and not going to say you how to solve the problem using it. How do we solve a original referent problem? How do we find string with this property using suffix tree or suffix array? Very easy. Take a look here. What is the like if I take any string, I can go down in a try until I find its position. But what's now the number of occurrences of this string? It's the number of suffixes in subtree. This is like obvious dynamic programming I can calculate. Second observation is, of course, it doesn't make sense to take the string that ends somewhere on the edge, because there is some other string that has exactly the same occurrences but is larger. So why not take the larger one if the number of occurrences won't change? Okay, so we only take strings that end in the nodes of suffix tree. So the answer to this is just maximum value among all nodes of the suffix tree of like CNT will be the number of suffixes in the subtree multiplied by depth of the node. But when I count depth, of course I count the total length of all edges, not the number of them. So that's it. This is how you solve a referent problem using suffix tree. In array, well, in the suffix array, what you can do is, I do not like, actually, I never like use suffix array because actually automata is pretty easy to code, and there is a also very simple algorithm how to build suffix tree using suffix automata. So anytime I need to solve something on the strings, I just write automaton and transform it to the tree and solve a problem on the tree. So I maybe already forget like good tricks how to solve problems with array. Let's see. We need to find, well, what is it? It's actually in terms of array. We need to find such segment that the value of its length multiplied by the minimum value on the segment is as much as possible. Okay, and how do we do this? Pretty interesting. I need to figure it out, actually. That sounds familiar, like we need to go and store all the minimums in the stack. And now I need to choose among them probably something like binary search works here. Or maybe, no. Okay, so probably you should figure out how to. Oh yes, I got this. You need to use like using suffix array. You go with the stack of minimums, and anytime you put a new element, you try it. So how do you like? What do I mean when I say you go with the stack? It means you have a stack with some values in it, and then your value comes. You threw away elements from the top of the stack until they are bigger than yours, or bigger or equal, it depends, maybe bigger. And then you put your element to the end of the stack. So that's how you usually find, for example, first element to the left that is strictly smaller or strictly greater or so. So you know, yeah, this technique. Okay. And now I claim that it's enough only when I threw away some element or put the new one to check the corresponding segment. Like, when I expel some element, I check this segment. When I expel this element, check this segment, and then I put it on the top of the stack, I check this segment. Of course, I can easily calculate the minimum as the minimum among these two and the length as the difference of positions. Why is this true? Because it's actually what you do when you traverse tree. Like, it seems to me like it's same as traversing suffix tree, just a left-right traversal. At least it looks so. And I remember something like this. Well, the good fact is we know how to solve refrain. The bad fact is we do not know how to solve the original problem yet. As I already mentioned at the beginning, this is the correct sequence of brackets. That's actually one of the definitions. So how to solve it using suffix tree? Now, it's not true that the answer is always ends in some node. Unfortunately, it can end on the edge. But for any edge, I can point no more than one position where at the end I should try. So let's take, for example, this edge. I know the difference, like, what is the difference of first, no, I should start from a different place. Okay, I was probably wrong when I said that this is just usage of standard things. You need to check you need to find all the nodes such that there is a correct sequence, at least correct sequence. It usually has the total sum, the total balance 0. But let's find all the nodes such that path from root to these nodes. First of all, its balance is not negative, and second, during this path, it never goes negative. So I can claim this path to be not the correct sequence, but at least some prefix, the prefix of some correct sequence. How do we do this? Okay, now we require segment tree actually. So, as you know, as I said, in compressed trie, for any age, I store the range of positions. Any questions now? So I know that going down this edge is equal to trying all elements on some positions, to adding them to the current string. If I know that at this node, I imagine I know the balance at this node, like the difference between the number of zeros and number of ones on this path, and also I know that it never goes negative. And now I want to check that first. If I add all these characters to the string, that it still be some prefix of a correct sequence of brackets. So it still never goes negative, and yeah, it still never goes negative. Okay. That it's not negative at the end is easy to check. Yes. That's just you need to pick the sum of the segments. Like you can replace zeros with +1 and ones with -1, and now you need only to check the sum here. But you also need to check that it never goes negative. And to do so, you need to calculate minimum on this segment, actually. Because the balance, you can describe it as some function that steps, like all the steps are +1, -1, and you need to check the minimum value and verify that the balance at the beginning plus minimum value on this segment is, well, actually, when I say minimum value, I mean the minimum value assuming you, like, if you have 0 here, I need to find how deep do I go. So the relative minimum to the beginning. So that actually will be minimum value on the segment minus value in the left end. Yes, and I need to check that this is not negative. If you think of it, it's pretty easy. Like, what happens? I go up and down, and what I need to check is that I never go below some line. So this is like minus balance of u is this line. I need to check it. I never go below this line. If at some point I do, that means the balance became negative at this moment. So this is how I traverse the tree now. How did so many teams manage to accept this problem? I also remember I coded it. It was like 3 years ago, but now it seems like, oh, I have to do. Well, actually, building suffix tree is not that big deal. If you remember the code of Automata, it's like about 15 lines, and I used to remember it just remember, you know, like you remember the poem. Not you start to think what I should write here. I just know what to type. And then you only take the reverse thing, build automata, take suffix strings, build suffix trees, build segment tree, traverse the tree. That's how here you're almost done. So now we know, what we know is for any node, I know if I can reach it. So whether the path that leads from the root to this node is still a prefix of some correct sequence brackets. So the final step is to check all the edges. So actually, if I know the balance in this node, I need on this edge find first position such that the total balance is 0. So that is, find first element that is less or equal than minus BU. And that corresponds to doing the same on the segment tree. So find first element that lies to the right of this position and is smaller than given. If you remember, this is exactly the problem about segment trees I used to tell you. And also I can say this is a coincidence. So that's not like I gave the problem on segment tree and then I started to choose the contest to show you that it really matters. No. And as you see, it's actually the second time you meet this during the camp. So I would strongly recommend to get used to do simple tricks with segment trees, because this is the most basic topic nowadays. Okay, I think we are done with this problem. Actually, I want to save some time for the lecture, but let me analyze one or two problems more. So there were actually only two really hardcore problems during this contest, I and D. I is icy rolls of normal. It's the worst thing of I is it sounds really easy, but it has just terrible solution. Like it's also pretty easy to code, but you need to think for a really long time. But we were lucky; we accepted it at the end of the first hour because we knew some related ideas, and that actually during the contest it almost kills all your opponents because you accept the problem, but it's actually almost impossible to invent during the contest if you do not know if you don't have any prerequisites. But the top teams see, oh, they managed to accept it and really fast. They're like, only 1 hour. Let's try to do this, and they try, and they fail. So that like gives you a huge advantage when you accept a hardcore problem at the beginning. I think F. It's nice. That's really nice, and the idea of the solution is nice. So let's analyze what is the theoretical maximum possible number of such angles. Like what we know that the sum of all angles in polygon will be equal to n minus 2 multiplied by 180. Also, now we want at least m angles that are 90 degrees. So we know that 90 multiplied by m plus n minus m. So okay, let's say that all angles that are not 90 are maximum possible. So I put 360 here. Like I can find always the angle that is as close as possible to 360. And we know that this value is greater than n minus 2, 180. Let's do some transformation now. Huh?
Greater, no greater equal.
Greater or equal? Because
360 is possible. Oh, okay.
Yeah, because 360 is impossible. That's why I like round it up. I'll see. Maybe I need to like. Okay, we'll see now. Now let's try to do something with this stuff.
You missed an n after the.
Yes. Okay. So what do we want? We actually want to have a formula that gives some upper bound on m given value of n. So I need to put all things with m in one side and all with n to the other side. So wait. Oh, no, it's okay. Okay, and I move all with m to the right, and that is 70m. So now I can say that m is less or equal then 180n plus 360 divided by 370, that is 2n plus 4 divided by 3. So that's the upper bound, theoretical upper bound on values, on possible values of n. What we are going to do now is first, well, that's not what I'm going to do, but what you should do during the contest. You should analyze small cases. Like, this is a typical trick. You prove the upper bound, and then you give the way to construct exactly this upper bound. So that automatically proves that your solution is optimal. That means if now we will give the way to construct exactly the same answer, then it will be fine. For small values, you need to try manually. 4 and 6 were given in the problem statement, yes. And like 3, 5, 7 probably try manually. It actually matters that we forbid angles equal to 180 because, for example, for 5, the answer is 3. But so I have 3 angles. But if I allow having angles of exactly 180, that means I can just put a point here and have 4. But we are not allowed. But now let's give the general case. That's the interesting part of the problem. So what we are going to do is we are going to pick some vectors that lie here in the 4th quarter and sort them by the angle. And add, of course, we are not going to take any two collinear vectors. So all the vectors have different angles. We sort them by these angles. And what we do now is I construct the following, like one node here and here. So here I use all these vectors. Okay, just for example, I'll take less amount of vectors because I do not want to paint. It won't fit. Okay. No, it's not bad. I want to choose the right picture. Okay, so this one is good. I construct the following. As you may see, I have 90 degrees here. And now I take any vector and replace it with that stuff. Like with these steps. So any such step, it adds 2 angles. And so what's the number of nodes here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 nodes. Okay. So for, and of course, if I add one new vector, it will add 3 new nodes, 3 new vertices. That is 3k plus 2. And the numbers of form 3k plus 2, if I put them here, it gives me 6k plus 4 divided by 3. Oh, this is of course rounded down. That is 2k plus 2 angles. The best I can hope to have. And here I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Wait. So something went wrong. Why do I have 9? Like, probably I did something wrong. Because the upper bound is, okay, I said 9 and k is equal to 4. Wait, k is equal to 4? This gives me I can maximum 8 angles, but I have 9 there. Something is really wrong here. So yeah, there are still 14 nodes. That is, the form is 3k plus 2, k equal 4.
You can choose pattern. Why did 3 plus 2?
What?
Where does the 3k plus 2 comes from?
3k plus 2 comes from the point that I can, if I add one new vector here, one new vector to this chain, that will give me plus 2 new angles plus 3 new nodes. So I only need to study the forms, the reminders modulo 3. So I take all the n's reminders from n modulo 3. But how did that happen that I got more than expected? Which probably means I made some calculations errors here, no? Yes?
On the left side of the column, that middle bracket, you can erase it and those two sides are adjacent to him. You can make only one of them. You can that upper tooth, the column. You can turn it to the
Yes. But that's not the case. The point is, I proved that I can't have I have no more than this number of angles equal to 90, and now I draw an example that has more. So it definitely means I have an error and I've made a mistake somewhere.
14 there is 10, so it's okay. Yes, for anywhere 5, it's impossible to go through the anywhere 4.
Okay, so, I put, well, okay, I have k equal 4 here, and actually, give me a second. Oh yeah, I did something wrong probably. I have 14 nodes. Again, I put it like it's 28 plus 4. It's 32 divided by 3. Yeah, oh, okay, I see now. It's 10. It gives me 10, so it means I do not have upper bound, actually. Okay, now at least I think things are fine here. But also I need to understand what went wrong. Yes, you are probably right. As the first vector, I need to take one parallel to x-axis. So this tooth, it actually will rotate somehow. It will work this way. So it gives me, now I have, wait, now this is like the case where I have 3k plus 1, because I have now 13 nodes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yes, I have 13.
Can you argue the same about the middle one? The bottom?
Yes, I can do the same with the bottom one. And now I have, yes, numbers of form of just 3k. So I have 12 there. I put 12 here. It's 24 plus 4, 28, divided by 3. It will be rounded down to 9. Okay. 9, and I still have 9 good angles here. And that means we know how to solve the problem for n that is divisible by 3. What the small modification we need to do now is try to solve it if remainder if it's a number of form 3k plus 1 and if it's a number of form 3k plus 2. So if it has form 3k plus 1, and for this case it's 13, I put it in formula. It's 26 plus 4, it's 30, divided by 3. Well, it's 10. So I should be able to somehow add one new node. What?
You can't get it when it's up to 360.
Oh, yes, you're right. It saved me from trying to do impossible. I can't, so this actually, it's strictly greater, and that means this is strictly smaller, and that means I cannot have inequality. So I can't have 10. I still can only have 9, and that means I can just add one more node to any place I want. For example, I can rotate this teeth, or I can make the step here. It doesn't matter. There are tons of ways to add nodes without increasing the number of angles. But if the number has a form 3k plus 2, things get worse. Because then I need to have plus 1, I have an additional angle equal to 90. Don't think that, so I need to add just 2 nodes and one more angle. One more angle with 90.
Create a new tooth with only 2 sides.
Create a new tooth with only 2. Yes, why not? Why not? I can here have the following. Like, so you suggested this? Yeah, why not? Good idea. Okay, so that's it. We try manually small cases when we estimate upper bound, when we construct these teeths, and try 3 different cases, 3k, 3k plus 1, and 3k plus 2. So that's it. I have like, okay. Very fast about problem C. It actually required you to understand how these numbers can look like. If you have number x plus number y equal to 10 to n, actually there are not very many ways these numbers can look like. So let's say they have same length, because I can put as many zeros here as I want. Like I allow to prepend numbers with zeros. Now it's easy to see that the general form of these numbers is the following. some suffixes of equal length are equal to 0. Like there are only zeros here. So the result of summation is also 0. Then follow exactly one position with the sum 10. Like if position of x plus if position of y, they have exactly 10. So you still have 0 here, but now you transform plus 1 here. And now from this point to the end, you have the sum equal to 9 at all positions. So this may be 0 plus 9, 1 plus 8, 2 plus 7, 3 plus 6, 4 plus 5, and vice versa. So the other thing you need to try is what will be the exact position of this happening. Then you understand how many zeros are at the end. Also, you need to check, you need to try all the possibilities to get 10 here. This is 1 plus 9, 2 plus 8, 3 plus 7, 4 plus 6, and 5 plus 5, and also other order. And now you have only to count the formula. So, how many ways are there to replace all the remaining question marks with numbers so that in this pairs you get everything right? So first you need to spend some question marks greedily to close the remaining position, and then it goes to formula. So, I'll let you figure out yourself what the exact formula is, because we need to make a break and to talk on computational geometry then. All the remaining problems, these are D, I. Oh yeah, also there was problem E. Oh, it's actually maybe easier than problem F. I just forget about this. Okay, I will try to include it in written analysis too. But of course, you want to. I recommend you not to expect the detailed analysis on problem I. I'll just give you main ideas, because the detailed analysis, like, I think one can write a paper about this problem. Because even during the analysis, Hinari was always like, oh, this was obvious. Okay, we just believe in this, and so on. And I did the same while solving it. So, okay, see you after the break.
I couldn't find the first contest on code forces. So could you send me the first 10 or 20 inputs and outputs of the big question?
Wait, how can you not to find it if the link to this contest on code forces is on the main page of our camp? Just go to the main page of the camp, choose day by day.
I've googled it.
Page,
I only find the NERC final.
It's not NERC. It's yes. But the main page says it's Moscow subregion of NERC.
Okay.
And yes, you need to try link.
Today I won't forget. Sorry about
Legal isso. Não, é legal isso. Botões. Ah, eu tenho saudade de botões, cara. Celular. Então, daquele negócio de slide, é possível no celular. É o link que eu falei que eu não podia. Você prova em uma hora. After that, he said that he's bad. You are partner of the university? You come along. Nice, very good. Are you graduating? But they... okay. Okay. It's all about training. Your team? Where is your team? Like me.
E aí, tranquilo? Problema aí. Mas uma coisa que eu não entendi, isso aí tudo fala que é coordenada inteira. Como é que faz isso com a coordenada inteira? Coordenada máxima. Não, você tem que achar, tipo assim, qual o ponto que faz mudar um integral. Só vai pro cheio padrão. Primeiro quando você achar que mudar 90 graus, faz tipo assim, você repete o padrão de baixo. A gente tinha feito qual isso daí. Dava uma menos, eu posso perceber. Só que isso daí é um pouco melhor que a escadinha, você aproveita um pouco. Mas é pessoal um pouquinho mesmo. Você queria que seja um negócio assim, 0, 0,2.
Yeah, 2 hours.
Talvez eu acho que fez uma escadinha também. Dá pra me colocar. Nós estamos no 8, cara. Vai sair do lado. Deve ser o caso dos plantão. Normalmente cresce exponencialmente o estado. O primeiro caso é o da entrada, o segundo é 10 vezes a entrada, o terceiro é 100 vezes a entrada, o resto é uma. Kleber, excuse me, how to draw this point on the plane?
Oh, I forget to mention how to choose,
Yes.
no, the points are easy to choose. The problem is to choose vectors. Like, if you know the set of vectors, then you just sort them. You just take some point that is pretty high, and you here you sum this vector. Now it's easy to do 90 degrees rotation.
Yeah.
Okay, so first what you do, you paint these pictures in this vector, and now you just replace all of them in this. You rotate it 90 degrees, next step here, bring this point, rotate 90 degrees to the right. I forget to tell you about how you choose the set. That might actually be
Yeah.
figure it out. Well, actually, the idea is take some small square and take all square here. Take all the vectors inside the square, such that no two vectors are collinear. And among two collinear vectors, you could choose the one with the smallest magnitude. And the actual estimation is that if you have like, if you want n vectors, you need approximately C to if you want n vectors, you need big square C to C. C should be approximating this is will be sufficient to look it up. There's other just actually what I do is I just go add one by one until I the limitations are chosen such that they're not. Yeah, I'm missing many details actually during analysis because I need you to ask me them and also they're limited. Could you call anyone outside to come in so we continue?
When I said suffix try, I meant the try of all suffix of the array. The try, not the tree.
Yes.
So, o coding algorithm builds suffix tree, not try.
Yes, but suffix tree it is try.
Ah, okay.
Try is just with letters
okay.
on the
Compressed.
edges. Yes, compressed.
Okay.
And Ukraine also builds a lot of other stuff. It also builds suffix links. It uses them, like, it uses them to work in linear time, but they are also very powerful for solving problems.
It is appropriated to code on a contest.
Yes, some people do, but I usually code suffix. You Google suffix automaton.
Okay.
And there is a way how to transform automaton to suffix tree. So the same one the Ukraine builds, I usually use this way. Like it's just faster.
It's faster.
It works faster, it's faster to code.
Oh, nice. I could explain how to solve this one.
It will take all the remaining hour, actually. I can give you the clue. Do you want the clue? Tips. And then I'll send written analysis with main ideas, but the clue is think of convex hull. So all the problems that were not explained, I will include them in written. And written on paper, they will be given to you, printed, and also it will be published on the site. I hope to finish. Actually, I promised you to make many problems analyzed and printed. Like there are now up to 9 problems. So, 12-hour long flight from São Paulo to Amsterdam will be enough, I think. Okay, let's continue. What are we going to do now? If we are going to analyze some typical computational geometry problems, like so-called fast geometry, like the ways to find some stuff faster than stupid approach. So I think that you are familiar with the following primitives, and you know how to work with them. These are points. Today I'll talk only about two-dimensional geometry. So points, lines. You need to be able to construct a line that passes through 2 points, to shift the line, to find the distance from a line to the point, to cross 2 lines. Circles. Main problems on circles are find common tangents of 2 circles, or tangent from the circle to the point. Okay, so these are primitives. Now let's start with which I consider to be the most common problem of fast geometry and the easiest one to solve. It is given a convex polygon, you want to do some pre-calculations. It will be better to do them in linear time. And then you want to be able, in log time, answer the queries whether the given point lies inside this convex polygon or not. So what's the main idea of this algorithm? That is, take any point For example, just like the first one. Or it will be better to take lowest and leftmost among lowest. Now draw the following triangles. And okay, here. What happens now? When you get a query point, you calculate its angle towards the angle of the chosen point. So, for example, this is the query. I calculate the angle. Now you check if this point doesn't lie in this range of angles. And actually, if you choose the lowest, in my picture I haven't. Okay, so let work your imagination, rotate this picture for a while, and think of this as the lowest point. That means all these angles, they are positive and no more than p. So you can easily check whether this angle is between these two or not. If it's not, then obviously the point is outside. Now, if the point is inside, you need to find which particular region it goes to. Actually, these are regions. You split the plane in two. And you need to find the particular one the point goes to. So, how do you do this? You just have a sorted list of these angles. And what you do is you do binary search. You do binary search and find two that bound this angle. That's it. So what we have a sorted list of angles. And two steps. Step one, actually 3 steps algorithm. First step is check whether the angle lies between. If it does, then do binary search to find the sector the point goes to. And now, when you have found the sector, you need to check whether it is inside the polygon or outside. So, I know the point lies here, but I need to check whether it lies inside this triangle. That's an easy stuff to do. You have to take this line and just see the distance to this line. If it's negative, okay, so let's say this is the vector of the line, I mean normal vector, like, don't know the name actually. If the distance is negative to the line, when you're talking about distances to the line, it can be negative. Usually you can treat the distance, to get the distance to the line, you just put the point in line's equation. And you should treat the value you get as the value you should shift the line to, so the point will lie on it. Okay, or maybe negative or positive, I need to check. Like, I always miss with signs, negative or positive, so I always draw simple examples to see what the sign should be. But of course, like all the points here, they have positive distance. Oh, okay, they have one sign, and all the points here, they have another sign of the distance to the line. So to be able to answer queries, you need to be able to get the equation of the line and see, oh, no, actually, I don't think you need really to build the line and equation. What you can do is you can take this vector and just get the cross product. Get the cross product of this vector and this vector. If one sign will mean that point lies here, another sign will mean the point lies here. So, if you do not like to work with lines, but however, I think this is pretty easy object to work with. you may just use cross product. So that's it. All you need to know we are able to check whether the point lies inside the convex polygon. Let's move on and do some other stuff with convex polygons. Now I want to solve the following problem. Given convex polygon, again, I want to do some pre-calculations in linear time again to be able to answer again in log time the queries of the form does the line crosses the given polygon, and if it what? Oh, good point. That doesn't seem to be the log time. I want to be able, given the line, answer whether the line crosses the polygon, and if it does, what are the crossing points? Intersection points, sorry. Whether the line intersects polygons. So, for example, this line doesn't intersect, this line does intersect, and this line does, and I want to know these points. So I can use this to answer what is like for the line. I can answer what are the squares of parts. I cut it. It cuts polygon into. But first I need to find this point. Here we will have two main steps in solution. Step 1. Find the point with maximum distance to the line and minimum. If we talk of oriented distance, like distance with sign. So for example, for this line, this is the point with minimum distance, for example. This is the point with maximum distance. For this line, this will be, I think, minimum, this will be a maximum, or vice versa, depending on what direction you will choose. But that doesn't matter. We just need two opposite points. If we have them, we now know how to solve the problem. So, second, I'll talk about the first phase later, because the second one is more obvious. Just intersect. So, first, how do you understand that the intersection even exists? You check the sign. If the signs of the distances are the same, that means the line doesn't cross this polygon. If the signs are different, so for example here, one of these will be positive, one negative. And for this example, both these 2 points will have, you have both negative or both positive sign. So that's it. Now you know if the intersection even exists, and you need to find it. Let me forget about the case and it doesn't exist and focus on okay. What I say is I have 2 consecutive sequences of nodes. One goes in clockwise direction from minimum point to maximum point. Another goes in clockwise direction, or from minimum to maximum in another direction, or from maximum to minimum in the same direction. So I have 2 continuous sequences of points. And from the one hand, I know that the sign is negative on one side, and the sign is positive on the other side. And also from lectures of calculus, I know that it means there will be some zero, because function is, and that's it. I don't know how to name this function in English. But that continuous, yes. So thank you, continuous. So that's it. We need to find where the zero is. How do they do this? Actually, they just perform binary search. Split this in the middle and see what is the sign. If the sign is positive, move the right bound here. Continue binary search. Again, divide in the middle. It's negative, I move left bound, and so on. When do I finish? Then L and R, they point to the neighboring nodes. Now I found two neighboring vertices that have different signs, distinct signs, different. That means I found the edge that is crossed by the line. Now I need to cross two lines and take the point. So, and now I do the second binary search for this continuous segment. So that's it. That's how you find two crossing points. And we can get back to the main problem. Find maximum and minimum distant point. In order to do this, we need to analyze something like, let's draw one more polygon. And now I'll take all the edges and orient them in some way. Set a direction. Okay. Now how do we describe the point that has maximum distance? So if I take this point, some point, and let's say this line, how do I know that it actually has a maximum distance? Because my polygon is convex, function of the distance to the line is also convex. Like if you traverse along the border, the function of the distance will look like the following. So you may see that it's convex to some point. Take the node, take the vertex, and figure out whether this vertex has the maximum possible distance. One is definitely do not. If the next vertex has bigger distance, or the previous one has bigger, yes? Then of course we are not the answer. But what if we do? Or not if we do, but if they are smaller. If the distance to the line here is smaller and here it's smaller. Like, okay, in this example, they all have negative values and they are smaller because they are bigger by absolute. Bad example. Okay, let's say these are the distances and I'm finding the closest point to the line, not the farthest. So I want to know, is it true that if my neighbors have bigger distance to the line, then I'm the closest point? That actually turns out to be true because the polygon is convex. So imagine they have bigger distance, but there is some point that actually has smaller distance. Let's move along the line until we find this point. And then we see that if I connect them with a segment, it breaks the definition of the convex polygon. So not just the convex set. What is the convex set? We usually define it as such set that any segment connecting 2 points lies strictly, not strictly inside, but inside the set or on the border. Well, it's actually you need to define the border. Well, let's not go deep in topology of these objects. So we know that it's enough to check whether our neighbors are greater than we. How do we check? That if you take a look at these directed edges, you will see that, no, you won't see from this picture. I'll need to draw something better, like, okay. So that is that picture. If you take the direction of the line, then it's the case, then the vector that gives the direction of the line, it lies beneath these two if you sort them by angle. So actually you see that you move along this vector, then you rotate to this one, and then you rotate to this one. And if it's not the case, if there is some node that is closer to the line, so here you can see that this condition doesn't work, that the vector parallel to the vector of the line, it doesn't lie between them. So, and that meaning that moving along this vector will take you closer to the line. So what's the algorithm finally? You write down or you write in some array all these vectors along like clockwise or counterclockwise traversal. And now to answer the query, you take the vector of the line and binary search for its position in this sorted array. Like actually, if you traverse along the polygon, you always turn right or left, depending on the direction you choose. Like if it's convex, you always turn right. So the total sum of rotation will be equal to 2p. So just break it at any point, write it in the array of its angles. Now take the vector of the line and find its position in the array. And this will be the point with maximum or minimum distance. Now how do you find another one? You change the direction of the vector of the line. If you do so, it also means that like the function distance, you also reverse it, change the sign, and again, you binary search the position of this vector in the array of sorted vectors of sides of polygon. Okay, so that's it. You need to do binary search 4 times to find intersections, but this is actually, there are different approaches, but I'm telling you the fastest I know, and I think also it's pretty easy to understand. Any questions? Yes?
How to avoid the problem if the line is parallel to one axis of the polygon?
There is no problem. If the line is parallel to the side of the polygon, that means you can take any vertex of this side, because they have equal distance. So it doesn't matter which one to pick. Question is here how to work with all this stuff. Like, do we need to calculate angles using a tan2 function? It's the question of taste. Like some people like to use angles at tan2. Some people, but be sure you use long double, not double, because double it has about 15 decimal digits of accuracy, and long double it has about 18 decimal digits of accuracy. So actually using long double can be as precise as using is doing everything in integers. But I strongly insist, if you know how to solve problems without using double, if you can have everything integer, do not use doubles. Because anytime you type double, you stay on the slight I. Oh, how to say? Slight i's or okay. Here you can, instead of having angles in long doubles, you can only just store these vectors and use cross products to understand what direction to choose. Well, it's just the matter of experience. How do you usually do? Like when you do convex hull algorithm, do you do it all in integers or you use doubles, for example? Okay, any other questions on this? Or we can move to other stuff. No. So the next topic is crossing semiplanes. Or half planes. I don't know which one to pick. So what you are given? You are given set of lines, but now the direction matters. So any line says you take the corresponding half plane. And what you want to do is you want to cross them all. So you're given this set of lines and you want like to find the polygon of points that lie inside all the half planes. Or I think semiplane sounds better. Do you know which one to use is better? Semiplanes or half planes? Okay, I'll name them semiplanes. Yeah, we are given some limitations, and we want to find this polygon. It's, well, two-dimensional case of linear programming, you know. The easiest simplex method ever. But still, the solution may be empty also. That's the first case. The solution may be unbound. The solution may be unbound but have zero area. And sometimes you really need to distinguish all these cases. So, for example, like if you have two lines, one pointing this direction and another line totally coincides with this one and points to the other direction, when from the one hand, you have unbounded, so like all the points of this line are the solution. The total area is 0, but you can find the point with big coordinates, as big as you want. The trick that really reduces the amount of work you need to do is adding boundaries. Like, if we know that everything we are going to do will happen in like some reasonable coordinates, then we just pick some value and add 4 bounding semiplanes. We add them far enough so they do not affect the answer. So if the answer was some normal polygon, then they won't affect it in any way. But if the answer was unbounded, then this will help us a lot. And also this will help us to distinguish different cases. Okay, let's find this intersection let's start from the stupidest complexity we have. Like, I think the most stupid solution here you can even imagine works in cube time. But I can't see anything that works slower. So n is the number of semiplanes we are given. How do you do this in cubic time? You notice that all the vertices of the resulting polygon, they are intersections of some lines. So what you do is you intersect all the lines, so you get n² points. And now for any point, you just check whether it lies inside or no. Like if it satisfies the equation of all semiplanes. This takes linear time for any point and gives you cube in total. Moreover, all the points, you do not need to build convex hull of these points then. You will already have the convex hull. Because there cannot be any point inside. If there is any point inside, then some of these points was chosen wrong. Because like, if there is a point here, that means there is a line here. But if there is a line here, if the line, if you are given a line that goes through some inner point of the polygon, that definitely means there is a vertex of this polygon that has negative distance to this line, following all this stuff about intersections. So that's it. The easiest algorithm in cube time. Next algorithm is, it works in square time, actually, the next one. So instead of taking all lines and finding all intersections, what we do is we add them one by one. Actually, this algorithm is the one I think you should know, because it's not harder in implementation than cube time. And it's much easier in implementation than n log n algorithm. And moreover, in almost all the problems of semiplanes that I have seen, it was, like, not almost, in many, it was enough to this work time. And implementing n log n crossing of semiplanes, it might be somehow hard. But I'll tell you how to do this in linear time with one trick. Not actually finding all the intersection, but okay. First of all, let's finish with square time. What we do, at any moment we store the polygon that is the current result. Like if I'm looking at the semiplane I, that means I have added all the semiplanes from 1 to I minus 1. Now I need to add the new one. Of course, maybe it cuts away some part of the current polygon. Actually, it may not cut anything, or it may cut away all the polygon. It just depends where you place this line. But we want to treat general case, then it cuts away some part. Because everything is convex, it's easy to see that you really need to throw away some consecutive segment of nodes, of vertices. And also probably create new ones. So the algorithm is just traverse the polygon and build the new one that is the intersection with the plane. So how does it work? You take some node, start from it, you look at it. Okay, does this node, does this vertex belongs to the intersection of this polygon and this semiplane? Well, yes, it does. So I copy it. You go along the edge. Does this point belong? Yes, it does. So I copy it too. Now you go here. Does this point belong? No, it does not. And that means that it just did, but now it doesn't. So we have intersection on this edge, on this. And I intersect the line with this edge and add it. I move forward. Does this? No, it doesn't. And this doesn't, so I do not do anything. Move on. This does belong to the intersection. That means I need to add it actually, but before adding it, I need to check this edge. I find the intersection on this edge, add this new point. Now move to this point, add it. Again, this lies inside, as same as this, so the whole segment is okay. And finally, I already know for this. I can't say I'm good in copying, so they look completely the same, but I think you got the idea. So what you just do is you take linear time to add one new semiplane. Actually, this time is not linear. The time depends not on how many semiplanes you have already added, but on how many points lie, so how many vertices are there in the current polygon. But of course you can construct the example, then it's also linear. Now, there are some ways to do this in n log n time. One of them is take a closer look on what other operations. Operation 1 is intersect a line with the polygon. Operation 2 is throw away some number of vertices and add no more than two new. Adding two new I can do in constant time. Throwing away some part will also work in, it will work in constant time in total, like in total do linear for n vertices. So the only thing I need to do here is I need to be able to find this line fast. So actually we can turn to this algorithm and use it, but instead of like here what we did, we first directed all the edges and we used to store them in an array. Of course we cannot use array now, we need binary search tree. So we use binary search tree to store the vertices of the polygon. And in this binary search tree we find 2 points farthest from the line. When we find intersections, well, that requires some code, that algorithm. Also, there is an offline algorithm of finding the intersection. And it even sounds easy, but it's actually not. The idea is let's behave in the same way we do when in the Graham algorithm when we build convex hull. Like we sort all the semiplanes we have by the angle. And now we start to add them. Like so at any moment of time I had the stack of the current points and current lines. And then I add the new one. It probably threw away some points and some ending lines. So that's a concept. That's how it's supposed to work. But then you will, like, if you try to implement, you will face that it's like the famous joke that in theory and practice are the same, but in practice they are not. Because first problem you will face lines with the same angle. Okay, you will keep only one line with the same angle, only the worst one. Then the second question is, how do I sort them, like if they're on the circle? Okay, so you break the circle at some point and sort them starting from this point. But this gives you the following effect, that the result you will have, it's not the... So imagine you continue this process. Yes, so you have the new, and at some point you want to end up with a polygon, but the problem is that it's not true that you need to throw away points only from the end. You also need to throw away some points from the beginning. If you do not, you will get something like this instead of the polygon. So the beginning, so this is what you will get if you just implement this algorithm. And now you need to throw away some stuff from here and some stuff from here. Yeah, now yes, now you end with a polygon. But that requires a lot of accuracy when you work. You need to be accurate and precise in understanding what's going on. So I personally did this only once. I used to store them in the deck. And anytime I add the new line, I try to throw away both from both ends. And this algorithm I actually never tried. I mean, no, of course, many times I did the static one, but when you need to store the convex polygon in binary search tree, many new tricks appear. But the truly cool thing I want to tell you is sometimes, the problem is not about working with the result, working with what you have after you cross all the semiplanes. Sometimes you only need to check whether it has positive area or no. Or maybe not positive area, you just need to find any point that satisfies to all the equations. And here is the very nice and linear algorithm how to do this. The idea of the algorithm is the following. I'll add semiplanes one by one, but in random order. So I do not use the order I'm given. I do the random permutation, and now I add them in that order. And every time I add the new semiplane, I want to know the toppest point, the point with the maximum y coordinate among all the points that satisfy to all the semiplanes. So for example, if the result is this polygon, then this is the top point. And when I add the new line, this maybe become the new top point, and so on. Actually, it doesn't matter that I store the top point. I just need to store the point best in some direction. But let it be the top point. What's going on now? I add a new line, a new semiplane. So I know that this is the top point. I add the new one. If it satisfies, like if this point satisfies this new semiplane, then I'm okay with it, and I do not do anything. Just like, it's okay. If I add a new semiplane, it can only cut away some points. So definitely, it cannot. New top point cannot appear. So I'm okay with using this one. And it may happen that it doesn't satisfy. So that's the case. What you have to do now is you have to find the new one. But the good fact is that you can claim that this new top point, it lies on this line. It's pretty easy to prove because everything is convex. So if you take a look at the picture again. So then this was the toppest point. It doesn't work now. And yes, as you see, the new toppest point, it lies along this line. You can imagine that it doesn't lie, and then you see that the original polygon wasn't convex. So let me not waste time on it now. Instead, let's see. How do we find this point? What do we do? We take, okay, I think I'm fine with erasing this now. So you know the line that new top point lies on it. You take all other lines, cross them, and then whenever you cross the line, two lines, you check whether this direction is good or this direction. So if it's about this direction, it gives you some ray. So actually crossing this line with all, when I say you cross it with all other lines, I only mean you cross it with all other lines that already were added. So if something is wrong on the line I, you check all lines from I to I minus 1. Oh, from 1 to I minus 1. So crossing with any line gives you the ray, for which you can claim that all these points are okay. And what you need to do now is you intersect all the rays. So you pick the rightmost in that direction and leftmost in that direction. Now you have this segment. You only need to pick the vertex of this segment that is higher. So you pick the top one. And now you have a new toppest point of the intersection of all semiplanes from 1 to I. Let's analyze this algorithm somehow. What is the work time? In the worst case, it takes square time, because any line will be processed in linear time. But really, adding if line will work in OI. And what's the probability of that to happen? Like, what is the probability that the toppest point will lie on this line? Actually, the toppest point, it is given as intersection of two lines. So what's the probability that my line is one of these two? It's 2 divided by I. So the total work time is I multiplied by 2 divided by I. That is equal linear time in total. Because the expected time to add one new line is constant. That's it. I really like this algorithm, but there is one I like even more. Vinicius told me that probably many of you know it. Who knows algorithm to find the smallest enclosed circle in expected linear time? Well, 2 of you. So it's probably worth telling others. So what is smallest enclosed circle? And this will be probably the last thing I'll talk about today. And actually the last thing I'll talk about to you during this camp. But I'm okay, this is a really beautiful algorithm. So we are given endpoints on the plane. And now you want to find some circle. So points, so y, r, and radius r, such that all these points lie inside the circle or on its border. and radius is smallest possible. So the point of the circle of the minimum radius that has all these points inside. And we will do this in linear time. First step is we take a random permutation of points and start to add them one by one. Now I take all the points one by one, and what I want to do after I take a look at first e points, I want to have the smallest enclosed circle of these points. So imagine for some I minus 1, I already have it. This is the smallest circle that contains all points from 1 to I minus 1, and I add the new one, the eth point. What may happen? May happen that it lies inside the circle, and of course that means I do not need to do anything, as I cannot make the circle even smaller, or the answer for I minus 1 was incorrect. Bad case is it lies outside. I say no worries. What that means is this point surely lies on this circle. It's pretty obvious. Like, if this point is the one that doesn't let the circle work. So if I take the optimal circle for the first e points, the eth point will lie on it. Like, it will be used. Because if it's not, it means I can make the circle smaller. And what I do is I simply solve the new problem. The new problem is you are given n points. Find such a circle that all the points lies inside. But now not n, now I have I. All the points lies inside. And also I know that eth point lies exactly on it. So let me denote this as, okay, no, better. So this problem is pretty close to the first one. It's a bit different. It just has a new limitation that I want the eth point to lie exactly on it. But actually, it's not limitation. It's because I'm given this from here. So like here, I'll only call this problem if I know that actually the optimal answer lies on this point. So I can remove this limitation. I know that this will work. But like, let's mark it with asterisks. That we have some additional knowledge. We have at least one point of the answer. How do we do this problem? We take a random permutation and start to add points one by one. So here, imagine I have like added all the points, first g minus 1 points. And this is the eth. So this is some circle. Now I'm adding the gif point. What may happen? Case 1, it's inside. And that means I do not do anything. Case 2, it's outside. Do you already have an idea what we do then? We have a third problem, yes. We call the third problem. And the third problem is you are given j points. find the circle of minimum radius such that all the distances are less than or equal than r. R is minimum, but also we are given 2 points of the answer already. So we know 2 points that lie on the that we need to use. So here we are now directly solving the problem. Like we fixed 2 problems. Oh, problems. Sorry, points. If they both these points lie on this line, what we can say is that if we take I don't know the English name for this line, but the line that is the line of the points that are equidistant line, maybe it's. So this is the line of the points that have the same distance to these 2. And now just take the third point and see what are the possible centers. Of course, the center of the new circle will lie on this line. So I just take all the points and see what are the possible centers of the circle such that this point will be inside. I find enclosed circle of these 3 points. This is can be done in constant time. This is standard problem. And I say that, okay, now this is the center, and for all the centers of this ray, this point is fine with them. So actually I take all the points and find this rays, and then I intersect this rays, and the last thing is I need to pick the smallest radius. Actually, I start to think that I can do the same. Like I can again pick them one by one until everything is fine. Okay. So here's some way to solve this in linear time. For example, you intersect the ray, and then you. Oh yes, of course. After you finish to intersect the rays, you need to pick the point of the ray that is as close to this line as possible. Yes, surely. The closer it will be here, the smaller the radius will be. So you need to pick just the closest point here. So I can solve this problem in linear time. When I go here, what actually happens? When I call this subtask 3 from subtask 1, it works in linear time. But what's the probability to call it? Like, what's the probability that the GIF point will lie outside? Any circle, it uses 2 or 3 points, like let's say 3, and one of them is already given. So the probability that point J it lies on an enclosed circle is 2 divided by I. Sorry, by I. No, not by I, by J, because I add them one by one. And the work time of the subtask 3 is OJ. So that gives me the total work time of subtask 2, linear of I. And now I go to subtask 1. What's the probability that the point will be outside? That means the new answer uses this point, and the probability the if point is on the answer is 3 divided by I. And the work time of subtask 2 is linear. So the total work time of the whole algorithm is linear. That's it. It seems to be cubic, but no. It turns out to be linear. This is what random permutation sometimes does. Okay, I think we are done for today, and actually my job on this camp is almost done. I have to finish. Yes, question?
Just a question. Who has seen this before? Only one? Because there was a problem with Brazilian first grade that used this algorithm at some point. Don't you remember? And no one remembers this. Seriously, I'm not that close.
Okay, so any questions? No. Okay, so see you on the contest and wait for the written analysis, and thank you for your attention to these days. I enjoyed giving these lectures.
Let's